I am Cooper Simon. My project director is Dr. Sara Neshani, and I am presenting on an FMCW LIDAR system for bathymetry. So the project is to create a portable FMCW LIDAR system for remote sensing applications to proceed by replicating the work of Gao and Hui, and the operating light frequency is 1550 nanometers, which is infrared. So bathymetry is the measurement of water depth at various places in a body of water, and it's difficult to do manually with enough data depth for river or ecosystem modeling, and drone systems allow for automated wide area measurement, and certain blue-green light frequencies can penetrate water, making LIDAR a viable option. So FMCW offers the advantages of lower power and timing precision requirements, while offering a much higher signal-to-noise ratio and being lightweight and using commercial off-the-shelf components. So for some background, FMCW stands for Frequency Modulated Continuous Wave. It's a linearly modulated frequency waveform, and the time of flight to and from the target creates a frequency difference between the return received at the LIDAR and what is being transmitted. And that frequency difference can be compared to the frequency waveform to calculate the delay. So the range equation is the frequency received is equal to 2 times the bandwidth times the range divided by the speed of light times the period of the waveform. And then the range resolution, which is the smallest distance that can be resolved, where 2 different objects can be resolved as being different, is the speed of light over twice the bandwidth. So here's an example waveform that has a 6 megahertz bandwidth. So it starts at 0 hertz and then increases to 6 megahertz. This is not identical to any waveform used in the LIDAR. This is just an example. So mixing is the multiplication of 2 cosine signals to create 2 new signals at the sum and difference of their frequencies, and it allows frequency up or down conversion, and you just use a filter to remove the unwanted component. So the LIDAR architecture is the laser is split, and half of it goes into something called an IQ modulator, which mixes the laser with the frequency waveform, and then the other half goes to and then the laser coming out of the modulator goes to the target, or in this case a delay line, and when it is received back, it is coupled with the unmodulated laser, and then the 2 signals are sent to a balance detector, which converts the laser signal into a radio frequency signal, which then the frequency difference can be found using an oscilloscope. So the frequency waveform is mixed with the laser. It's then amplified and sent to the target, recollected, mixed with the unmodulated laser, converted to radio frequency, and then remixed with the frequency waveform to obtain the frequency difference. So the modulator takes the input, which is the laser, and then it creates a component that is in phase with the laser and a component that lags the laser by 90 degrees, and then it outputs the sum of those 2, and by changing the coefficients of the 2, it can change the phase or frequency while preserving a constant amplitude. So some current progress has been focused on tuning the frequency waveform and characterizing accuracy, and this has been done by performing test rangings. So the current frequency waveform that is in use is a 5 microsecond pulse that goes from 0 hertz to 1 gigahertz. And here is a graph of the signal. So as you can see, at time 0, it starts at 0 hertz, or an extremely low frequency, and then rapidly increases to 1 gigahertz. So a focus has been testing the frequency waveforms and different periods for the waveform on 2 different delay lines to see what provides the best accuracy. And the two delay lines are a 0.67 microsecond and a 17.75 microsecond delay line, which correspond to ranging a target at 100 meters and 2.6 kilometers respectively. So the setup, in the top left, there is a digital oscilloscope, which is used to find the frequency difference and thus the range. Below it is the waveform generator, which generates the frequency waveform. In the bottom right, there's the delay line, which simulates the target. Above it and slightly to the left, the silver object is the modulator that mixes the frequency waveform with the laser. And then above that is the laser diode, which creates the laser. So here's an example frequency spectrum showing a 137 megahertz frequency peak for a 5 microsecond 1 gigahertz waveform on a 0.67 microsecond delay line, which corresponds to a calculated delay of 0.69 microseconds, and the expected frequency to have been received from the 0.67 microsecond delay line would have been 134 megahertz. Here is another example from a 17.75 microsecond delay line for a 100 microsecond period, 1.6 gigahertz waveform, where the center receive frequency is 283 megahertz, which corresponds to a 17.69 microsecond delay, which is much, much closer to the actual delay than the result from the previous ranging. And as you can see, the expected delay for the actual, the expected frequency for the actual delay is 284 megahertz, which is a difference of only 1 megahertz. So here is a graph of the results of testing the 0.67 microsecond delay line. The orange is the measured delay using the LIDAR, and the blue is the measured error. And the scale for the measured error is consistent with the next graph, which shows the much, much lower proportional error for the longer delay line compared to the shorter one. So the theoretical range resolution is the lower limit on accuracy, and for a 1 gigahertz, it's the lower limit on error. And for a 1 gigahertz bandwidth, that corresponds to a 30 centimeter range resolution, which puts a lower bound on error for the shorter delay line of 0.3% and a lower bound on error for the longer delay line of 1% of 1%. So the next steps are to digitize the received signals so they can be post-processed using MATLAB on a separate computer, which will allow better accuracy and precision and increased bandwidth. And then further down, a goal will be to convert the system from IR to blue-green so it can be used for bathymetry. Also to miniaturize the system so it can be mounted on a drone for aerial bathymetric surveys. Here are the references, and then are there any questions? Yes?
So I was once watching this fishing show, and they were using some device to also estimate the depth. Do you know anything about that? Were they LIDAR based, or what are the other technologies? And can you compare like those technologies to like the precision or accuracy you may get with LIDAR?
Typically, if it's used for fishing and off of a boat, that would be an echo sounder, which is sonar. And I know one of the primary reasons that those are used is because you can get echo returns off of schools of fish to locate fish. I am unsure of the accuracy differences between sonar and LIDAR, but one of the advantages of LIDAR would be that it does not need to be in contact with the water. So you can get aerial results.
So why does the longer delay line have so much less error than the shorter one?
So a good reason for that could be the bandwidth of the laser itself. So the laser diode doesn't output just one pure frequency. It will output several across a narrow bandwidth, and that can cause error in the system. And for a shorter delay line, which will result in a lower frequency difference, the frequency difference from the laser will be a more significant part.
So I'm wondering why you're using the 1550 nanometer infrared light if you'll later need to change to the blue-green light.
1550 nanometer laser light is used in commercial fiber optic communication systems, so it's relatively easy to obtain components and slightly less expensive. And there are already a lot of literature out there on producing LiDARs from 1550 nanometer components. So it was a good proof of concept.
Do you know what the limiting factor on the accuracy of the LiDAR system is?
That would be the bandwidth of the frequency waveform, which in the current setup is limited by the bandwidth of the analog to digital converter in the oscilloscope. And recording the signals and then post-processing them later on a computer will help increase that limit, because currently the ADC bandwidth limit has to be split between the frequency waveform and the received results from the LiDAR, whereas with post-processing you can have a previously digitized frequency waveform and expend your entire bandwidth budget on just the return from the LiDAR.